Maddie, make sure you grab your exam. They're up here. They might be on that side, either here or over there. I think Maddie, yours is over there, if I'm not mistaken. Yeah. All right, it's 9 a.m. I'm assuming some people are going to be a little bit behind because of weather, but we're going to get started. Make sure my microphone.
Not sure if fun driving here.
Yeah, it was fun this morning, wasn't it?
Oh yeah.
Yeah. All right. So let's talk about the grades on exam 2. I told everyone historically exam 2 grades are lower than exam 1 grades. That was not the case here, but I think it was because, well, I'm pretty sure it was because I offered that bonus question that was worth equally weighted. So there are 6, I graded the first 6 questions. Each problem is worth 10 points. So you could have got 60 points. Does that make sense? It's just easier for me to grade each problem on a 10-point scale. So you could have got 60 out of 60 would be 100, right? If you got that basically means each problem is worth 16.7% of the grade, each problem, all right? So if you got all 7 correct, that's 116.7. That's the highest possible score. We did have that, okay? So we did have someone complete the entire exam correctly, every problem, all right? And then we had a lot of, look at how many A's we had. 10 A's, I think, 10 A's. So the blue is exam 1, the orange is exam 2. So we actually had more A's on this exam than we did on exam 1. We had fewer B's, fewer C's, fewer D's, more failing grades, all right? The class average for this exam was almost an 80. On exam 1, it was 77.7, so the average went up. This is the number that's a little depressing for me, though, the standard deviation. So I talked about this on the first exam. The standard deviation is like how closely my students' grades are to one another, how close people are to the average. And so if you have a small standard deviation, that means everyone's clumped up together. The exams are up here. Just come grab if you can see it there. So the smaller the standard deviation, the more my class is like all together. The bigger the standard deviation, the more spread out the grades are. As you can see from the big orange bar here and the big orange bar here, right? That means I've got a big spread of grades. So it is what it is. I mean, it's, Greg, your stuff's up here. You can pick up your exam. I think it's right here, actually. This is my, like a Halloween picture there for you. All right, so I was very pleased with these scores. What else do I want to say about it? Yeah, I don't know. I don't know what else to say. There it is. So I think for a majority of the class, a big group of the class here, first 2 exams have gone pretty well. The third exam is historically, the third exam has been better than the second exam. So we'll see how that goes. It might be worse in this class. Can't figure it out yet, but. And then the final's always the worst one because it's chapter 8, sequences and series, and that's always the hardest exam. And so I think for a lot of you, you've set yourself up well so that you're ready to get into the harder stuff. Yes?
Is the final exam going to cover everything we've done in the class or just the last few chapters?
Final exam is almost completely chapter 8 because there's just not enough, even in a 3-hour final exam, because it's 3 hours, that's still, I need all of that time to make sure you understand sequences and series. So I'll pull a few little things from previous material, but not a lot. So it's cumulative, yeah, kind of. When we get to sequences and series, you actually have to do some integrals in there. So it's kind of built in a little bit, but not much. Does that answer your question? Okay. Any other questions or comments? Okay. Well, if you didn't do well on this test, or you've had a couple of tests now that haven't gone well, please come, see me. Make an effort to come sit down with me in my office hours. Let's talk about where you are in the class. Let's talk about where we go from here. What can change? What's best for you? All right, so let's get going here. We're going to get down to Chapter 7. We're going to start Chapter 7. I'm going to do a quick review of kind of where we are with everything, and then we'll get into Chapter 7. What am I doing here? So I'm going to put what Chapter 7 is up on the board. Remember, everything I put over here on this TV screen, these are in your notes that you can access, right? So Chapter 7, Section 1. So what we're doing in Chapter 7 is applications. We're going to start to apply what we've learned to figuring out different things we can do now that we know how to do antiderivatives. And so Chapter 7, Section 1 is areas between curves. So we're going to get into that. All right, and today's going to look very familiar because it's going to be really tied into stuff we've already done. All right, there's just one slight little tweak. So I want everyone to just take a moment to recall where we are right now. Okay. So recall that we established the definite integral, right? We used the fundamental theorem of calculus to say that this is equal to this, right? And geometrically, this represents the area underneath a curve, or between a curve and the x-axis, right? And it gives us like a net area, right? It counts areas below the x-axis is negative, areas above is positive, right? So that geometrically was take some function f, started at A, ended at B, and then what we're doing is we're finding that area in there, right? So the big thing I want you to be putting together here, and it's not so much for Chapter 7, Section 1, this is really for the next section, the one after that and the one after that, this is not the first time I've said this, is to remember that what we did here, this formula, right? The f of x and the dx geometrically means something over here, right? The f of x was do you remember? Or the height, I'll call it the height of the rectangle that we're going to draw on there, and this is the width, right? So we imagine that we have a rectangle in here that has this infinitesimally small width to it, right, dx, and the height of it was just the function's value, right? And the distance from here to here, that distance from the y-axis, from x equals 0 to here, that is what x is. All right, so what we're doing is we're saying, look, we're going to take all these rectangles, height times width, that's area. We're going to add them all up, and we're going to start x at A, and then we're going to end when x gets to B. So I want you to see this rectangle, this little infinitesimal rectangle, starting here. We find that area, and then we just keep adding them up as we go from A to B, and then we stop, right? Add all those up, and that's your area. And it turns out that the fundamental theorem of calculus says just calculate that, and we've got it, right? So, yes? Today, oh wait, I wanted to tie one more thing. So after we did that, the next thing we did was improper integrals, right? So when we did improper, there were two types. And I only want to talk about type 1 right now. Type 1 was the one where you either go from a to infinity, right? Or you went from negative infinity to, I don't know, let's say b, or you went from negative infinity to infinity, right? Those were those three different types, or three different scenarios we could run in with the type 1. So these visually, it's the same picture as this, right? Except that we're either going to keep going that way forever, or we're going to keep going that way forever, or we're going in both directions forever, right? That's what this was. All right, so that's where we are, yes? All right, so now what we want to talk about are areas between two curves. Between two curves. So what I'm going to do is start this with a picture. All right, so 7.1. Let me draw you a picture of the scenario I want us to kind of investigate. What if we have, let's say, some function f, okay, like that. And then we have some other function g. And let's say g does this. Now, first thing I want you to kind of agree with me on is that these are both functions of x. What I mean by that is back in college algebra, when you're learning what a function is, right, we would say that both of these curves pass the vertical line test, right? And because they pass the vertical line test, both f and g can be considered functions of x. You give me an x, I give you the y value, right? So I'm gonna put here f of x, just so it's clear that these are functions of x. And there's g of x, all right? We're interested in the area in here, right? We want to know this area. So I want to shade it, but I also am about to draw a rectangle. So let's just say that right there is what we're trying to find the area of. So what I'm going to do is I'm going to do it exactly the way that we set up the definite integral in the picture that I just erased a second ago. We're going to start, we're going to set up an integral. It's going to add up a bunch of things, right? So this is about to add up a bunch of things for me. And what I'd like to do is start it right here where they hit each other, right? At that intersection point, I'm going to let that be the a, all right? So I'm going to start adding up, starting with x being a. And then I'm going to stop when I get to the point that they intersect here, b, right? Now, what I'm going to add up are a bunch of rectangles again, right? But the rectangles I'm going to draw are going to be slightly different than what they were before. Slightly different, not a lot. But imagine we have rectangles that are going to start here and go across. I'm just going to go pick like an arbitrary one. Just imagine this one right in here. Okay, imagine that right there. I would like to know the area of that, right? So I should have done this to the side. Let me move this over. Okay, so this is where we are, right? And I want you to kind of see, I'm going to take, this picture is very cluttered. There's a lot of stuff going on here. I'm just going to help you and me see this, I'm going to just redraw it. Here's my x-axis, right? This is my x-axis. I have a rectangle right here, like this. That's that rectangle right there. Then I have, on top is the blue curve, right? And on the bottom is the red curve. Yes? I want to know the area of that little rectangle. All right? I want to know the area. So would you all agree first that the width of it should still be dx, like it was prior to this, right? So I know that I'm going to have the width here, dx. That's my width, right? And now what I need is the height, right? I need the height of the rectangle that I'm going to add up. So how tall is this? Well, we know the distance from here to here, right? That's just the value of f, right? That's f, the function f, that's how tall it is, right? And then what's the distance from here to here? G of x, right? And so the height that we're interested in, right, is this, which is what?
F of x minus.
It's this one minus this one, right? It's just the difference of the two. So it's just f of x minus g of x. So that's what goes here. F of x minus g of x. Let's put that in parentheses, right? That's the height of that rectangle. So what I'm going to do, what this thing represents now to us is we're about to add up a bunch of things, right? It's a bunch of heights times widths. This is the formula for the height. This is the formula for the width. I'm going to start with x being a, and I'm going to stop when x gets to b. So I'm going to start over here. X is this distance from here to here, right? X is going to start at a, and it's going to end at b. Is this clear? Yes? If it seems almost too clear, it's okay. Don't worry, because 7.2, we need to be able to understand this, like really understand this, all right? So, all right. So really, when we look at this, what do you think seems like it's going to be the most complicated part of it then? The what? No, it's okay. I mean, what's different? What's different? I mean, we're still going to have to do an antiderivative, right? And we'll use the fundamental theorem of calculus, just like we did before, right? What's different here is these 2 points, right? That's an additional thing that we're going to have to kind of deal with, right? We're going to have to figure out where these two functions hit each other, right? Find an intersection of two curves. That's something we haven't had to do up to this point, right? I just gave you a function. I said, hey, let's go from here to here, and then that was it. You never really had to figure out where to start and stop. Here, we're going to have to figure out where to start and stop. So let's do an example, yeah? But this is it. This is the formula right here. That's the general formula. If you ever want to know the area between two curves, okay, and I do need to say this, f of x is bigger than or equal to g of x, then this is the formula you'll use. What is this saying?
If it's basically the top.
Exactly. This is saying that the f function is above the g function. In my picture, the f function was on top of the g, right? So as long as the f is on top of the g, that's the formula. If g is on top of f, that formula changes by, all that happens is this changes, right? That's all that would happen. All right, let's do it. I'm going to make that a little bigger so you can see that. All right, sketch the region bounded by y equals 2 minus x squared and y equals negative x. So one thing I'm going to advise is that from here on out you have your graphing calculators, because if you don't know how to graph something, what are you going to do, right? Now, these I expect that you would know how to graph. Y equals 2 minus x squared and y equals negative x. These are both functions of x, aren't they? How can you tell they're functions of x?
They both have x.
No, they both have x, yes. That doesn't mean it's a function of x, though.
The y is singular.
The y, we've solved for y. Okay, because both of those equations are solved for y, they are both functions of x. In order to determine what y is, all you have to do is feed me x, right? Give me x, I'll tell you what y is. That means that they are functions of x. Okay, so I need to draw these real quick. All right, I hope you know what this looks like. Y equals negative x, right? That's the negative diagonal. I'm going to graph that. Okay, this is y equals negative x. Goes through the origin, right? And then the other one is 2 minus x squared, right? This is, x squared is a parabola. Negative makes it go down, right? And the 2 does what to it? Moves the whole thing up 2. You could, if you want, not look at this way, but look at it as negative x squared plus 2. And then it's your parabola going down up 2. All right, so I'm going to draw that. I go up 2, 1, 2, here's 2. and I draw my parabola. It comes down like this, goes like that. All right, got it? I'm not being super precise right now. I'm just getting a general picture of what's going on. Does everybody see the region? It says sketch the region bounded by those curves and then find the area. Everyone see the region? Yeah? All right, so, oh, I forgot to label what that was. That was y equals, all right, negative x squared plus 2. I'll write it like that. All right, so here's the region that we want to find the area of, right? This is my region in here. So I'm going to draw myself a rectangle, just so I have it, okay? I'm going to just draw myself some arbitrary rectangle in here. I could have drawn that rectangle anywhere I want. I decided to put it right there. And then, again, to help myself, I'm going to draw the x-axis. I'm going to draw the rectangle over here. I'm going to see that the red curve is always the one on top. The blue curve is always the one on the bottom. And so I can tell which one's the top one and bottom from this, right? The red one's on top, the blue one's on bottom. So I'm going to call the top one, this one, I'm going to call that one right there. Well, I'll bring it over here. I'll call that my f of x function. F of x equals negative x squared plus 2. And then my g of x function will be equal to negative x. And then I can just use the formula, right? Now, I do need the limits of integration, right? I need to figure out where a and b are. So I need to figure out where they hit each other. So how do you figure out where two curves hit each other? You set both of the curves equal to one another. In other words, if y is equal to this and y is equal to this, you set these equal to one another, and that will be where they hit each other, right? So I'm going to do that right now. I'm going to find the intersection of the two curves by setting them equal to one another. Negative x squared plus 2 equals negative x. That's a quadratic equation, right? That's a quadratic equation, and we know how to solve quadratic equations. We usually just move everything to one side and then hope to factor, and if factoring doesn't work, we use a quadratic formula, right? So I'm going to move everything to the right side because that's a negative x squared, so I'm going to leave that over there, 0. Make this x squared minus x minus 2. So move those two terms over. Does it factor? Minus 2 plus 1. And now set each of those factors equal to 0, and you get your two solutions, 2 and negative 1. So these two graphs will intersect each other like this point right here. I didn't know what it was, right? But I can tell from there that's negative 1. And over here, I can tell that that's a 2. The only way I know that is by solving that equation. All right? Question? Yes?
Are you going to want us to be able to do this without drawing a graph?
I'm going to give you graphs you should be able to draw. Now, your homework might be more complicated, and then you'll need your calculator. But everything I give you on a test would be something that I think you should be okay with. Now, you can use your calculator to help you, all right? But just know that I don't feel like I'm going to be trying to push you too hard on the graphs. Yeah? Okay, so let's set up the integral. Ready? Another question or no? So the integral is now going to go from negative 1 to 2. It's going to be the f of x function first, which was for us negative x squared plus 2, right? I'm going to write it like that. That's let me write it like this. That's f of x. And then I'm going to subtract from that g of x, right? But g of x was negative x dx. Look at the way I wrote that. Here's f of x minus g of x, right? I put it all in parentheses, and then dx. Let's clean that up algebraically. Let's just clean this up. This is really integral negative 1 to 2, negative x squared plus x plus 2. So all I did there was made that a plus, right? And I just decided to write it in descending order. You don't have to put it in descending order, but I did. Negative x squared, then the plus x, then the plus 2, dx, right? And that's it. Can you handle that antiderivative? Yeah, this should be a pretty straightforward antiderivative at this point. I'll put it over here. So fundamental theorem of calculus now, right? The antiderivative of that should be negative 1/3 x squared plus 1/2 x squared plus 2x. And then we put the evaluation bar, -1 to 2. This all looking familiar at this point? Yes? Oh, cubed, yeah. I said cubed, I wrote squared. I think I said cubed. Thank you. Okay. Yeah? Which number do we plug in first? 2, right? We got to plug in 2 first. All right, let me do that. So now from here, this is going to become, all right, let's go. 2 things get plugged in there. So when I plug in 2, 2 cubed is 8, 1/3 of 8, so -8/3. 2 squared is 4, half of 4 is 2. And then 2 times 2 is 4, right? Then you plug in -1. Be real careful with this -1. What's -1 cubed? -1 still, right? And then times -1/3, +1/3. So you get +1/3. And then -1, when you square it, you get 1. Then half of 1 is still a half. So you get +1/2. And finally, -2. Almost there. -8/3 plus 6 -1/3 -1/2 plus 2. So I just put those two together, distributed, and let's see, unfortunately, let me see, can I put those two together? What's that? -9/3, right? Which is -3. So I have -3 plus 6 -1/2 plus 2, right? All I did there was those two together to give me my -3. 3, 5. Is that 5 minus a half? I think so, right? 5 minus a half, which is 9/2. 4.5. The area between these two curves is 4.5 square units, whatever they are. Feet squared, inches squared. No one gave me any units, so it's unitless right now. Good? How about this one? Sketch the region bounded by y equals the square root of x, y equals x minus 2, y equals 0. And then once you sketch the region bounded by all of those, find the area. So y equals square root of x, y equals x minus 2, y equals 0.
And it's okay, like during a test, you can go back and calculate and just write the graph listing using the graph calculator.
You can use that as a guide, yeah, and then draw the graph, yes. But as a Cal 2 student, you should be able to graph those. Like if you can't graph those, you're kind of kidding yourself a little bit right now. This is a line and this is a square root function, right? These should be pretty, I'm not saying like they should be right off the top of your head, but by the time you get to the test, this should be like you shouldn't be reaching for your calculator to graph this. This right here looks like, it's like a weird sort of, I'm going to do it in blue just kind of now to get some color on the board here. That's basically what the square root function looks like, right? It's almost like a parabola that's been cut in half and laid on its side. Okay, that's this one, right? This is a line, right? What's the slope of that line? Slope of the line is 1, right? This is y equals mx plus b. So that's, slope is 1. The -2 is the y-intercept. So I'm going to go down 2, 1, 2. That's -2. I'm going to draw a line with the slope of 1. I'm just going to eyeball this, all right? I mean, I'm not trying to be perfect here. There we go. Got that? Right now, is there a region? Do you see a region bounded by anything? No, there's no bounded region, right? There's nothing bounded. Like if y'all know that, I don't know if this is common knowledge, but have y'all ever seen that tool like on Photoshop or Paint? It's a bucket. It's a little bucket with, like you're spilling paint into something, like a fill. It's a fill feature, right? Like if I were to go right here and click fill, it would go and fill the whole place up, right? Because there's no bound, it's not a bounded region. So we're trying to find the area of the shade of the region bounded by these three curves. I do need this still, right? This is actually what? What is this graphically? It's the x-axis, isn't it? This is the x-axis. I have green here. Let's see if this green works. Oh, it works. Okay, so the green would be the x-axis, y equals 0, which is this. All right, now do you see a region bounded by all of them?
Yeah.
Yes? Right here, right? That's it? Okay. Do y'all see we have a problem?
Yeah.
What's the problem? Yeah, so imagine you draw a rectangle. Remember, the whole idea was to draw a rectangle and see what the formula would be, right, for that rectangle? If I draw my rectangle right here, what's the function on top? The square root, the blue one, right? And the function on the bottom is the y equals 0, which is the green function, right? As I start sliding from left to right, is it always going to be that way? No. When I get over here, now what happens is the top one's the blue one, but the bottom one's the red one. You see that? So there's a change. I need to account for that. So how do you think I can do this? Okay, that's option 2. We're going to talk about that after we do this. Two integrals. Yeah, why don't we just do two separate integrals? One that goes from here to here, and in that one, it'll be blue on top, green on the bottom. And then when we go from here to where they hit each other here, right, then it'll be blue on top, red on bottom. That seem reasonable? Okay, let's do that. Now, we need to figure out some points here. We need to figure out where these points are, right? So I need to figure out what that is. I need to figure out what this is. I need to figure out what this is. Some of these you can just do without solving anything, just by looking and analyzing, right? We know what this point is, right? 0. What about this point? 2. You can tell that it's the x-intercept of this line, right? It's where this hits the x-axis, so set it equal to 0. X minus 2 equal to 0 gives you 2. So that's 2. Am I going too fast? It's okay? It's all right? How about this one? How you can get that one? That one I'm going to solve, all right?